Hello, differential equations students, and welcome to Chapter 7. This is Unit 3, okay? And we're going to get into Chapter 7, and we get into these Laplace transforms, okay? And what happens here is we're going to end up taking a differential equation. We're going to take a differential equation right here. We're going to apply an operator. Okay, basically what happens is we're going to apply this operator and we're going to transform it almost into like a different kind of dimension. We're going to put it into a different space. And when I do that, it becomes an algebraic equation. Then we can use all of our different solving techniques for algebraic equations. Okay, we'll solve that. We'll solve using our algebraic equations. Right? And then what we'll do is we'll actually just invert it. We'll take the inverse of the operator, and then we'll have our answer. Okay? So basically we go from a differential equation into a Laplace using an operator. We solve using algebra, and then we put it back into a differential equation. So then we do like the inverse. Okay, that's what we're going to be doing. Okay, of course the big thing for today is just figuring out how to perform these operations to get it into Laplace, okay, which are called Laplace transformations. So we'll start here. We'll start here with our, and it says that, let me get this out of my way. We're going to put it right here, will be good. So let f of t be a function defined for t is greater than 0. Okay, so t has to be greater than 0. The Laplace transformation of f of t, and then we have this Laplace of f of t is equal to this big F here, which we've seen this thing before, right? You've seen this idea here before. Where did you see it? Well, that was when you actually were given the first time you did an integral. We let this be like big F prime, so then the inverse of this, or I'm sorry, the integral of f of t is big F. You have seen it just like that. Okay, well, t goes from 0 to infinity. Okay, we're going to evaluate that. Oh, okay, and then we have the definition here, which is e to the negative s t times f of t, and we have a dt. Okay, of course, it's not necessarily important that you know where this comes from. This is the definition. We could, of course, do a formal proof and kind of a research to figure out why this works, but kind of with the shortened day here as far as the snow day, I think I'll just go through why we have it. And we have s has to be greater than 0 here. And that's the definition. You need that down. You are going to have questions. Okay, I am going to have quiz questions and test questions, okay, over using the formal definition. You'll have to be able to use the formal definition. And now I think I'm ready to, find my very first one. I want to find the Laplace transformation of f of t equals 1. So when I'm looking at this, I want f of t equals this 1. All right, well, let's see here. Before we wrote this weird L here, that's a Laplace of 1 then, right? Which if I set it up, that means that I'm taking the integral from 0 to infinity of e to the negative st times, this is a 1, so there's a 1 right here. And then I have, what was it, dt is my variable. And now we just have to integrate. We have to integrate this. Of course, we're all very smart here. We know that this thing times 1, we would just get this thing, right? And then next, okay, well, what's the integral of e to the negative st? Well, s is not being integrated against, so it's just a regular old number, which means that's 1 over s, negative out front, and then e to the negative st, evaluated from 0 to infinity. Now I just have to do some, simple, hopefully anyway, simple math here. I'm taking the infinity in first, so it's technically negative 1 over s, e to the negative s times infinity, then minus a negative 1 over s, e to the negative s times 0. And I'm kind of running out of space here, but I think I can move this up here. Well, here, think about what's happening now. This infinity times this s. Well, that makes it a big number, but then it's negative. So it's actually, this thing actually looks like negative 1 over s, and it's times 1 over e to the, basically, if it's s is a number, and infinity times it, well, really, that's just e to the infinity, essentially. Right? That's just essentially e to the infinity. Well, what's 1 over a huge number? A huge number. Of course, you know this here. It's as it approaches the biggest number ever. This thing right here, you do know this. You studied this in pre-calc. This thing right here is going to be 0. Which, of course, then makes this whole entire show 0. So then I have 0 minus whatever this is. Oh, well, it's a negative, negative, so it's a plus. Then I have 1 over s. Well, e to the negative s times 0, well, that'll be e to the 0. Oh, well, then I just get 1 over s. So the Laplace, oh, I don't want to do my L's like that. The Laplace transform of 1 is 1 over s. Okay. Now 1, that was a constant, right? That was just a constant, and we got 1 over s. So there's your first one. Well, let's try another one. Let's try to do another one here. Now I would like to do the Laplace transform of t. All right, so now I have a variable t, which this means this is equal to 0 to infinity of t e to the negative s t dt. All right, now when we look at this, right, I'm going to need to get some smaller. Here, when I look at this, now this becomes, right here, this is an integration by parts. U should be t. It makes du equal to dt. I would have dv is e to the negative st dt. That makes v negative 1 over s e to the negative st. And okay, well, now I just have to remember it's what? uv minus v du. So I'll have uv, that is negative 1 over s t e to the negative st minus the integral. V is negative 1 over s e to the negative st du, which is dt. Okay, and we can simplify this a little bit. I think this is 1 over st e to the negative st plus 1 over s integral of e to the negative st dt. If we evaluate this, we have negative 1 over s e to the negative st. Right? And I shouldn't have drawn, this is my mistake here, right? Technically, right here, I should not have drawn just this. This is from 0 to infinity. And here, remember that this is from 0 to infinity as well. Okay. Now, as I work down through, I get this thing. Okay, but then I have to take this times 1 over s, right? And then I can drop the rest of this jazz right here down. So I have negative 1 over s t e to the negative s t plus. And going very slowly here for the first couple times, I wanted to go real slow, so hopefully you can follow really easily. Here, this is negative 1 over s t e to the negative s t. Distributing the 1 over s, I would have a negative 1 over s squared e to the negative st. And then this whole thing, I still have to evaluate from 0 to infinity. Now, I'll try to go, kind of as slow as I can. I want to plug this 0 in, and I want to plug in this infinity. Of course, order does matter here, right? So I'm supposed to plug in the first one minus the second one, or is it the second one minus the first one? Of course, you know the answer to that. You're supposed to be plugging in this infinity here first. Now, if you plug in an infinity into a negative exponent, that makes the bottom thing huge, right? That makes it huge. So because it's huge on the bottom, what is going to grow faster? So here, maybe I'll try to slowly do this one here. We have a negative. It's a t. Okay, a 1 over s infinity times essentially 1 over e to the negative s times infinity. Now this one's kind of tricky here, okay? This one's kind of tricky. What is growing faster? Is this infinity going to grow the top faster, or is this e, and this is a positive now that's in the bottom, is this e times a number, some number s that's bigger than 0, now bigger than 0, guaranteed, right? All the way back up to the definition. It's guaranteed to be bigger than 0. So this is still a giant number to a power of e. This bottom part, right, this thing here that I'm boxing is growing faster. If it's growing faster on the bottom, plus I have another an s down here that I multiply by, that means that the bottom is going much, much faster than the top, which makes that term right there 0. Okay, and now the same idea is held when I take this infinity and I plug it in for this section. Hopefully you can see my cursor here, this section here. So I have 0 minus 0, and that was for my infinity. Now, of course, I have to do my 0 next. Okay, so I have a giant minus sign. Then if I take 0 and I plug it in over here, well, again, maybe I'll go through one here slowly. 0 up top there, e to the negative s times 0. Well, that'll make it e to the 0, that's 1. This 0 times whatever s is, it's not even going to matter because that's going to be a 0. Then I take the same thing, right, and I plug it in over here. So maybe I'll write this one out. That is a negative 1 over s squared e to the negative s times 0. Well, that's e to the negative s times 0. That's 0. E to the 0 is 1. So I have minus 1 over s squared. Of course, you can see there's a bunch of zeros here. So it's 0 minus, a negative. Well, that will make it a positive, which means that a Laplace transform of t, what we set out to get it was 1 over s squared. Okay. Now we've done 2 Laplace transforms. We just did Laplace transform of t, and then we did one of 1. Okay, well, we can kind of see like a slight pattern. I'm sure that if I asked you, hey, what's the Laplace transform of t squared? At this point, you'd probably say it's 1 over s cubed. I mean, that just seems very logical to me, okay? So this would be like a hypothesis, right? We have this hypothesis, and now, of course, we're going to test it, right? We're going to test this idea, and we're going to go through the same process. This time here, I'll try to maybe pick it up the pace a little bit. So I have the Laplace transform of T cubed, which would be equal to 0 to infinity T cubed e to the negative st dt. Of course, here, this sucker right here, this thing right here, isn't the funnest thing to integrate because I have to do integration by parts a bunch of times. There is a slight trick we can use. What we would be doing would we would be having u be t cubed, and then we would have our dv be that e to the negative st. And I can't speak as to if Mrs. Bond showed you this in BC, but there is an easy way to do this. We actually just continue to take this u and we make du's out of it, which will end up being, 3t squared, and then 6t, and then 6, and then 0. Okay, well, how do I know how far to go? Well, I have to go until I've exhausted all of the powers, right? I'm exhausted all the way out. Then over here for my dv, I just continue to do that. Well, that's 1 over s e to the negative st. Remember that you're taking the integral going backwards here. So the next one would be, oh, I don't want that negative in there because if you had a negative times a negative, I would get that to cancel out. And that'd be 1 over s squared. And then I have e to the negative st. Then the one after that would be negative 1 over s cubed, e to the negative st. Then finally I'd have negative, nope, it wouldn't be a negative. It would be a 1 over s to the 4th, e to the negative st. Okay? And I think she would have shown you something similar to this. And then after this, what we do is we actually take this top one. I know it's going to be u, right? I take this du, and I end up mixing it. Oh, it's u times v. Oh, well, this is v down here. So it's this times this. This times this. This times this. And this times this. The only trick that we have, or the only thing that we have to remember here as we're trying to use this trick, the first one of these, okay, I have a positive number, right? So like it's this thing, as I'm going down here, it's just uv. Oh, okay, so I just take this one as it is. But then after that, because it's u v minus v du, the next one will be negative. This one will bounce back to positive because I get this negative again, which makes this one a positive. So it's like I have a positive, a negative, a positive, a negative. Okay, and now when I go through, again, I'm trying to show you this kind of quick way to do this because it is very simple after you get it down the first time. Here I am taking this thing times this one. Okay, so I'd have negative 1 over s t cubed e to the negative st. Then I go down to the next one. If I get a different color here, try to help you out. Now I'm taking this one, those two times each other, but remember this is negative, so it'd be a negative in this case. And it all just depends kind of how you want to write this. I think I'll try to keep it decently split apart. Okay, and there it is. And then, of course, we're just continuing, right? We'll continue to work down. So my next one would be, okay, it's a plus here, but it's times that negative, so it'll be a negative 6, 1 over s cubed t e to the negative st. And then finally, my last one I would have a negative 6, 1 over s to the fourth, e to the negative st. And we are evaluating this thing, this whole thing, right, from 0 to infinity. Okay. And so here we go. When I'm plugging in on this infinity, right, I'm going to take this infinity and I'm plugging it into all of them. Well, look, they all have this e to the negative, e to the negative, e to the negative, e to the negative, which means this whole giant thing is 0. Minus, okay, now I have to plug in 0. Well, if I plug in 0, this t right here makes this whole term 0. This t right here makes this whole term 0, so minus 0. This t here makes this whole term 0. No t here, though, so it's minus, what, 6 over s to the fourth. Six over s to the fourth. Okay, well, then I do some math here, and it looks like the Laplace transform of t cubed would be equal to, negative, negative, so this will be 6 over s to the fourth. Okay, 6 over s to the fourth. Now, what have we found so far? Let's see here. The first one we did, Laplace transform of 1, that was 1 over s. The Laplace transform of t was 1 over s squared. The Laplace transform of t, we didn't do squared, did we? We said we were going to do that. I didn't even notice that until just now. The one I just did was what, t cubed? That was 1. No, it wasn't a 1. It was a 6 over s to the fourth. Well, our logic on the Laplace transform of t squared was going to be 1 over s cubed. But clearly it's not just a 1 up here. Clearly this one has a 6, right? This one has a 6. Well, how could I rewrite 6? That could be written as 3 times 2 times 1. And then over s to the fourth. Well, here I have t to the first power. Well, 1 could be written as 1, and then this is s squared. Okay, well, if I try to use this, I don't think that this 1 here would belong. Instead, it's got to have a number. Well, it looks like this one was 3. It had an s to the fourth, right? Oh, well, then if this one is 2, it has a 3. I like that. But it looked like up top here went 3, 2, 1 for this 3. Oh, well, then up here, I wonder if it's a 2 times a 1. Which, that just so happens to be the case. The general, okay, the general form of a Laplace t to the n power is equal to n factorial over s to the n plus 1. Okay, this needs to be somewhere in your notes. You can easily find it. You need to have this memorized. These are one of the Laplace transformations that you're going to need to have memorized. Okay. Of course, here then we have some Laplace transform. I think now would be a great time in the video to pause it and get these properties down. Okay, get these properties down. So now that you've had a chance to get those down, these two here are going to be mainly covered in 7.2 as they are really used with the derivatives, okay, with the derivatives. But, you know, I just wanted to give them to you now. You do see this f prime and f double prime. That's the derivatives, and we're going to get into that on 7.2. Okay, let's go over this linear operator idea here. Basically, it says that I can split them up, right? I can split them up, and these alpha and b's and betas, okay, we're assuming that these are constants, okay, which just basically means, you can just take them out, right? You can take them out. So if I was doing the Laplace transform of 4, say, right, then that would be equal to the Laplace transform of 4 times 1, which means that I have the Laplace transform of 1, which we already found would be 4 times 1 over s, which most notably we probably are going to write as 4 over s. Okay, just that simple. Now I do want to try an example here. We have an example. Make sure you get it copied down. I don't think I had enough space before for you to copy it down. So I have it copied down. And we're going to attempt this, right? So I have this Laplace. This thing here, I couldn't get the software to write my goofy L here. So remember that it is the Laplace. This would be 3 Laplace of t to the 7th plus 6 the Laplace of whatever sine of 8t. Okay, hopefully that setup there isn't too much for you. And I definitely want to conquer this one here because that one should be rather easy, right? That's just 3 times 7 factorial over s to the 7 plus 1. Of course, the 7 I'm getting here from t to the 7th. Now the next one here, we haven't actually conquered this like sign here. All right, we haven't seen that. So this brings up a good point to talk about, and it's the idea that we're going to use some Laplace tables. Okay, we have some Laplace tables, and specifically, when we look at the table, oh, that's not what I wanted to bring up. When I look at the table, I'm looking for sine. Well, I see it right here, right? I do see the sign, so it looks like it says a over s squared plus a squared, right? S squared plus a squared. Again, we can kind of see it. It's just sitting right here. So let's go back then to our idea. Well, it was s squared. Well, let's start with this 6, then, oh, I shouldn't have done it in that color here. I have my 6 times the Laplace of this thing. Well, we said it was s over, no, it wasn't s, was it? It was a, see, now I've already forgotten. It was a over s squared plus a squared. Well, the a in this case is the 8. So I would have times 8 over s squared plus a squared. Oh, that's 64. Okay. And now this thing right here, okay, technically you have transformed it. What has happened is you've taken this, okay, or you've taken this thing that is in terms of t and you've transformed it into like this s variable, okay, into this s variable. Notice that there are no super complex functions in here. Like there's no sign inside of here. Okay. Now a big thing is we could simplify. We could simplify this if we wanted, right? We could combine these 3 and this 7 factorial, this 6 and this 8, and we could even put these all over stuff, okay? That could be done, but right now we're just working on transforming things. Okay, I already talked about that. So I have this example here that I'd like to do, and then these 4, all right? These 4. I don't want to take up a ton of time. The video is already 30 minutes here almost, but I do think that it is important to get through some of these, so maybe we'll do these just kind of a little bit faster. I'll try to not do the colors changing as much and things like that. So I want to find the Laplace transform of 5t, which in the back of our mind, right, we should know that this is going to be 5 over s squared. Well, okay, so it says that I have to use the definition, so that's 0 to infinity of 5t e to the negative st dt. Well, then I know that that's 5 times the integral 0 to infinity of t e to the negative st dt. I would have a t e to the negative st. This would be a 1, a 0, negative 1 over s e to the negative st, and 1 over s squared e to the negative st. I know how this works here, right? I know that this thing's going straight down times this, so that's negative t 1 over s e to the negative st. This should have had a little negative there. Then I take this one times here. Of course, I have to be careful. I know that this goes positive, negative, so this is a negative 1 over s squared e to the negative st. Then I have to evaluate this from 0 to infinity, not forgetting my 5 sitting out here. And if I plug in infinities, again, we've talked about this negative up here. That's going to make the first thing 0 minus, oh, there's a t here, so when I plug 0 in, the first term is 0. Then this one here, this will become a 1, so it's minus 1 over s squared. Well, this is a positive 1 over s squared, but I can't forget that this was all times this 5, and lo and behold, we get the same thing. Okay. Moving on, find the Laplace transform of each of these functions. Okay, well, so I'm taking 9, the Laplace transform of t cubed, minus 5, the Laplace transform of t squared, plus 6, the Laplace transform of t, minus 4, the Laplace transform of technically 1 here. Okay, and we're just going through here. I know t cubed, okay, t cubed, so then I know that that's going to be a 3 factorial over s to the, well, it's 3 here, so it's a 4 down here. Then I'll have this one here, same type of logic here. This is 2 factorial over s to the 3rd. This one is technically 1 factorial over s squared. And then this is 0 factorial over s. And if I just fill in the stuff that I had out front, so this is 9 times that, minus 5 times that, plus 6 times that, and minus 4 times that. And of course, we could, maybe we'll simplify this one out. These numbers aren't too big. As I'm thinking about this, 3 times 2 times 1 is 6, times 9 is 54 over s to the 4th, minus, what, that's 10 over s cubed, plus 6 over s squared. And now what's 0 factorial? This actually was covered all the way back in like algebra 1. This is a counting principle. Okay, 0 factorial, this thing here is always equal to 1. So this is minus 4 over s. And there I have my Laplace transformation. Again, just kind of moving forward, moving down through these. Okay, here I think you'll start to catch a little rhythm as you get going. But here I'll write it out again. So this is a Laplace transform of 7 times the Laplace transform of e to the 6t plus 11 Laplace transform of e to the negative 4t plus 9 the Laplace transform of t e to the 2t. Well, all right, now I got these new ones, right? I have some new ones here. I haven't seen that before. So again, we got to go to the table. This is posted on the site. Okay, so what was I looking for? This is e to the 6t. So I need e to some power. Oh, right up here, number 2. Looks like whatever the power is, I'm taking, so e to the at, and then I take s minus a. All right, that doesn't seem overly difficult. Let's see here then. So I have a 7 times, there's my a is here, so that would be what? 1 over s minus that thing, which is 6. And then we just keep going, right? So like if I did this one next, that'd be 1 over s. It's minus negative 4, so it's plus 4. hopefully that doesn't seem overly difficult. Now this one over here though, of course, have to throw a wrench in our system here because we got this t there. So now I need to go back to the table, and I'm looking for something e to something. So I need something times that e out front. Oh, I see it down here, right down here, right? I think I see it right here. All right, I see it right down there. Looks like n factorial over s minus a, then n plus 1. Okay, I think I can do that. Okay, let's try it. So this, right, it was supposed to be whatever that power of this thing was, so that's a 1 there, over s minus whatever this a is, which is 2. Oh, and then this is to the 1, so then it's like I add another 1 to 2. Similar to here, this was for my, up here we had a squared, we did s cubed down there. It's like this thing here is taking that spot. And we fill in the rest, plus 11 times that thing, plus 9 times that. And I think we can do a little bit of simplifying. You don't have to do a whole lot here. This is 7 over s minus 6 plus 11 over s plus 4 plus 9 over s minus 2 squared. Okay, and then we're on to the last one. This is going to be my last one for the whole video. Like, that's the end of the notes. Okay, so here, let's break it down. We have a 3 Laplace transform of cosine of 5t plus 7 Laplace transform of sine of 11t. Well, we already did the sine one, right? That was whatever it was, so 11, divided by s squared, and then it was plus that thing squared, so 11 squared is 121, and then I have my 7 times that there. Now the one we haven't seen is this cosine, so we got to go back to the tables. Let's look for the cosine. It's somewhere in here. I saw sine here. Oh, cosine's right here. This one's different. It's got an s up top. Instead of the number, it's got the s. Otherwise, it looks the exact same. Okay, so up top, it's got an s instead of the number. Then it's s squared plus whatever it is. Oh, it's 5, and squared is 25. Then there's a plus technically in between here. And if we were to simplify it just a little bit, this is 3s over s squared plus 25 plus 77 over s squared plus 121. And I warned you last class that you need to make sure that you know how to do partial fractions. And you can see that we already are starting on that route. We're already starting to have a couple fractions split up. So again, please review your partial fractions. But that completes 7.1, which is the intro to transforms using the Laplace technique.